My name is Fraser Tooth. I study MNG Electrical and Mechanical Engineering at the University of Strathclyde, and today I'll be speaking on my fourth-year individual project from last year, which is titled Small-Scale Energy Harvesting from Linear Flow Using Electromagnetic Induction. So first I'm going to go over the motivation and aims behind the project, then the supporting theory and the design I eventually came up with and subsequently built. Then I'm going to discuss the testing and then the results of those tests, and then compare the device to other devices on the market and suggest improvements and draw conclusions from that. So, what is energy harvesting? Well, energy harvesting is extracting power from the environment, and it implies a low energy system. So you see this in rural areas in places like Africa, such as this kind of system, but a lot of the time in countries like ourselves, you're looking at small sensors that people don't want to be connecting cables to because they're in remote or hostile environments, or otherwise just small power systems that maybe need a few more watts. So the conventional remote power systems, transmission lines, they do carry some losses, and they're also quite expensive and have rather large environmental impacts due to their size, essentially. Generators, they're subject to the availability and price of the fuel that you're going to use for them. And if you're going to use large batteries, then obviously they can take quite a large physical space, or they require, and they also require to be replaced regularly. So the aims of this project were to design an original energy harvesting module. I was limited to using only electromagnetic induction, so solar cells, piezoelectricity were out. I had to generate at least 1 milliwatt, so that's enough to power a small wireless sensor, kind of roughly. Kind of keep costs low and within budget, and test in a wind tunnel and assess the potential of the device. So. Frankly, linear flow is uncommon in practice, as I'm sure you're aware. Flow will come from multiple directions. Really, linear flow, you're looking at maybe a duct and a river at best, but like, we assumed linearity to simplify the design for the basis of prototyping. So when you're extracting energy from linear flow, you're using either lift or drag. So a horizontal axis wind turbine uses lift to turn the blades, and a cut anemometer, your wind speed measurement, that will use drag. However, there's another type of system you might be able to use called Aeroelastic flutter, which the wind belt developed by Humdinger Energy does use. So I found out through this phenomena through their design. So Aeroelastic flutter, if you've ever taken a class in structural mechanics, you probably have heard about the Tacoma Narrows Bridge disaster, where a bridge in the US began bucking and weaving over the course of a few days before completely collapsing. Opinions vary, but some people reckon that it was caused by aeroelastic flutter due to the wind interference on the bridge. So it's based on the harmonic oscillation of an airfoil. It requires some elasticity in the system, and it generally works at a specific wind speed. I has a specific sort of harmonic wind speed it tends to work best at, but generally it can be seen in a bit of a wider range of speeds. So I'll just go quickly through aeroelastic flutter as a system. So as the airfoil, you've got it here, and the wind is coming from that direction, the airfoil lifts up. But if your leading edge is being dragged towards some midpoint, the airfoil will naturally turn, and the lift will change direction and force it down, and subsequently pulling it back to the midpoint over and over again. You end up with this oscillating stroke where the lift force is sinusoidal over time. So I've got a short video here showing you, it's a bit adjusted, but show it how it this can be a real big one as you've got parts of the tailplane which are threatening to fall off. So usually in aerodynamics, you're trying to design this out of your system. You don't want it to happen. You design it in speeds where Mach 1, like where you will never fly at. However, we're trying to encourage this for the purposes of extracting it as an energy resource. So essentially, we're making a driven, underdamped oscillating system where we're trying to maximize the kinetic energy so that we can draw that kinetic energy out of the system by maximizing the frequency if you're looking at generator speed, or the force if you're looking at some sort of gear system to do that with. So the design that I came up with has an aerofoil, which is allowed to rotate and also move along a rail system. So it's got 2 degrees of freedom. Now, the clever part about my design is balancing the force over the aerofoil. Now, all the forces that act on the airfoil and lift can be centered around one specific point. That's called the center of pressure. It's seen 25% along the chord, where the chord is the leading to the tail edge. Just draw an imaginary line. So with a symmetrical airfoil, at this point the net moment, the turning force, is 0. In a non-symmetrical it becomes more complicated. However, so for a symmetrical airfoil, if you hold the airfoil at that point for any angle that you're facing the wind at, facing the wind at, the minimum will be 0. That's called the quarter chord theorem, as the diagram shows sort of the balance of the forces over an aerofoil. So how does this work in terms of my design? Well, that point where the aerofoil is pinned, it's allowed to rotate, that is at the quarter chord. So when the lift force is acting upon the aerofoil, it's not trying to turn it in any way. The lift force does not cause a turning force on the aerofoil. It means all the lift force, ideally, is acting along the railing, acting along that linear motion. So the stroke is able to extract the maximum amount of energy from the oscillation of the aerofoil. So this was the model that I designed and built, and it uses a rack gear drive. So as you can see, you've got the rack gear that drives a small generator there, and then it uses a sliding bushing, and that's your standard student project elastic band holding everything together at the front. So stuck it in the wind tunnel. It's a rather large wind tunnel, so we can, sitting it in the middle, kind of avoid the boundary effects of the turbulence, so that wouldn't affect on the testing. I don't know what your wind tunnel is like at Edinburgh, but at Strathclyde it's pretty old and rickety, but it generally does the job. Okay, so hopefully this will run. So this is the increasing speed test, so just looking at the cut-in speed, and then what happens as you increase the speed up to higher levels. So at 6 meters per second it starts to cut in, and that's kind of what it likes when it runs. It kind of looks like when it runs. That's from another angle as I start to increase the speed past 6 meters per second. So as the speed is increased, the frequency of the oscillation begins to increase as well. And then, so I added a rack gear to sort of prove that it is able to drive, and I took a linear force off the rack gear and as to how much it was pulling at particular points, at a particular point in the stroke cycle. Apologies for the jitteriness of the video, but in general, just giving you an idea of what it looks like when it's driving the generator. And that's at 15 meters per second. So here are some graphs that I built from that. As a frequency test, as we saw earlier, the cut-in speed is around about 6 meters per second, which is quite high, but we'll get onto that. Also, the curve is non-linear because it seems that as the speed increases, it has obviously a less subsequent effect on the frequency of oscillation. As for the linear force test, it works in the other direction. It's an exponential curve. However, when you got up to the really high speeds, the flutter began to spasm somewhat. It began to flicker at the edges. So it kind of suggests that the flutter kind of breaks down at the high speeds, at least for this particular system. So it'll probably peak at some point. Then I added the generator. There's a small DC motor run backwards as a generator, just kind of proving the point. And then I used a small gear to up the speed to a reasonable amount. So the generator test, it's running. So funnily enough, we've got a DC motor putting an AC output into the oscilloscope, and I think it was around about 6 meters per second. Put it at the start of what we're running at right now. So as you can see, it's fluttering along, driving the rack gear, which is driving the axle of the motor, creating a AC waveform. And this is me increasing the speed, so as you can see, the amplitude of the signal increases as well as the frequency. So the generator test, using a matched power load, I was able to get the power output from the small generator. It's pretty low. We're talking at a sort of standard speed of around about 12 meters per second. You're looking at around about 13 milliwatts, which is very low, but just to prove the system. But it follows a similar trend to force, so it'll probably peak as well as the flutter begins to break down at the high speeds. Another interesting thing which I looked into was that I found that changing the elastic stiffness of the elastic band changed the frequency and the amplitude of the oscillation. I did a test with that because I didn't have masses of particularly good equipment with which to sort of step measure the stiffness. It was quite difficult to do so. But in any case, as you can see from the small bar graph, changing the elasticity made some relatively dramatic effects on the output, which is could form the basis of an active control system whereby measuring the elasticity at certain wind speeds can help to maximize your output. So in order to compare the systems, we must look at the power and wind. I'll just quickly go over that. So the power output, power available on the wind is half times the density of the air times the area covered entirely by the turbine. In the case of my device, it's a kind of square rectangle shape, and then cube of the speed. And the power coefficient is how much energy from the wind is converted into electricity, around about 40% for your standard HOTS. The comparison, so my electrical to mechanical efficiency of my small generator, the small DC motor, was around about 2%, comparing it to the power from the I was getting from the rack gear itself. So I'm going to use mechanical power to compare, assuming that a reasonable efficiency of generator could be found. So the power is the linear force, which we could measure earlier, and the frequency, which we could also measure earlier, times the wavelength, which is the stroke, the length of the oscillation. So the power coefficient was an average of around about 4.3% after the cut in speed. And this, for its size, as you make horizontal axis wind turbines smaller, you begin to lose your power efficiency and cost efficiency, but really it should be double that, if not a little bit more, to be competitive in its own market. So, so suggesting some improvements, there was a lot of stickiness on these rails that I was using, so that would have to be reduced. A potential way of doing that, instead of using a bushing with lubricant, using a linear bearing would be ideal. Also improve the generator, obviously, in order to get some useful output, and then potentially use an active control system to maximize your power output at specific wind speeds. Now, the viability of the system. Going any bigger isn't likely. The high vibrational loading caused by the oscillation caused some cracks, as I was beginning to notice in my model. And that was after only maybe 4 hours of testing, maybe more. But that may have been to do with manufacturing, because I think that bearing was kind of hammered into that hole, so I'm not entirely sure. But frankly, a horizontal axis wind turbine is a lot less complicated. However, if you're making it smaller, these sort of stress issues become less of a problem if you're using certain types of materials. So, making it smaller, if the power coefficient can be maintained, it can win out against the competition of some of the other research that's available. So, just to go over things, we need to eliminate the need for transmission lines and batteries in hostile and remote environments. My design uses the core-to-cord theorem with aeroelastic flutter using an induction system. The module operates as expected, and it provides an average mechanical power coefficient of around about 4.5%, but it needs to be at least double that, so maybe around above 10% to be competitive. So in general, for these kind of devices, you need to aim smaller and use some sort of control system. Thank you very much, and if you'd like to ask any questions.
Okay, so thanks, Fraser. Again, another very interesting talk. We now welcome back our advanced students. I think they also knew their colleagues were presenting soon. But yes, I'd like to invite any questions from E&M and control engineers particularly. So, Aristides, you like to start?
Hi, very interesting. Good job. I have a question about the loading of your generator.
Yeah.
So, how did you calculate the power that we're getting out? Did you just...
I matched the power load to the small generator, which was around about like 12 ohms, the generator itself, and did the matched power load calculation.
So you just put a fixed resistor basically on the terminals of the little motor?
Yeah, and then matched the power.
Did you consider something a bit more advanced, something like a maximum point tracking? Because...
yeah, I didn't... a lot of my time was spent developing the turbine and getting in the test, so I didn't manage to complicate the generator system in any meaningful way, unfortunately. That's something that I've been criticised for before, but in any case, it's something that I know is a weakness in the way I conducted my report at the project, but obviously that would be the next stage in terms of trying to get meaningful power out of the system.
Because I think that you will find that you can actually get more power than what you show in the results if you try to actively match what you're getting out of your little motor to what's happening on the blades. So use something like a maximum power point.
Okay, matching power point.
Something.
Excellent, thank you very much.
Yeah, and you also mentioned something about stiffness.
Yeah.
You were trying to match the stiffness with...
So it's judging by the sort of minimal test that I did, it seemed that changing the elasticity of the point of the whatever, maybe a cord, maybe a bungee cord of some description, bringing the leading edge back to that midpoint, changing that elasticity, changed the power output. And I feel that if you have, I'd need to obviously do a quite a large range of tests to see how stiffness affects it and what speeds things are best at, but you could create a sort of PID system where it is matching, almost like a pitch control system where you're matching the stiffness of the chord, so imagine like dragging it in to make it stiffer and then lifting it loose to make it looser, to specific wind speeds where it may be you may be getting better power than other stiffnesses, because I think it affects the frequency and thereby the sort of force that you're getting out of the oscillation.
Well, no, you continue. I might just ask if anyone else has any other questions at this stage.
Adam, can I just ask you to speak up at the front, because we can't really hear at the back, so it'd be great if you could
Okay.
louder. Thank
Good.
you.
We have a new audience, so we all need to speak louder.
Super,
Okay.
thank you.
That was not a question for Fraser. That's for me. So Sasha, if you'd like to, we've got time for a quick.
Besides concerns about the output power and energy, I have some concerns about the input power and energy. So the hydrofoil is changing the attack surface or area to the energy, and we actually have a pretty complicated relationship to find out for each angle and each dynamic going from one to another, what is the input energy. I know you can define the drag force, but I have to say I was a bit disappointed to see that you took the heart of design figure from the website. www.dynamicflight.com.
Yeah, well, that was.
It was not yours, so let me finish what I'm saying. So what I would expect is that you have a really good treatment of that if you are ending up, and this is now getting to my question, with few tenths of milliwatts output, and you recommended not to go bigger, to go smaller. And I'm just actually wondering here, for what purpose we can use these energy harvesting with a system of that size, providing, say, on average with 4, 5, 6 meters per second, providing maybe a few milliwatts. So what you intend to supply with this, assuming that there is still no conditioning. So you still regulate certain level of voltage and current at the output of your generator to supply some loss. So there will be some losses in the conditioning after you connect some generators. So could you please explain that?
Quickly, please.
All right. So, like, the power output from that small generator was around about 15 milliwatts. However, I was calculating the power coefficient from the linear force that I got from the rack gear. So I was using a sort of mechanical power calculation, and that was much higher. That was in the watts category. That was around about 6 watts, but I didn't list that. So it was a bit high, but then you've got all these transmission losses and everything else. Essentially, naturally, I need a lot more time to figure a lot more things out.
Okay. That was a good conclusion. Right, okay, so thanks again to Fraser for a very interesting talk.
This production is brought to you by the University of Edinburgh.